we'll talk about the Kemperman inverse problem.
All right. Thanks, Christian. If I'm not wrong, for the introduction, and thanks for letting me sharing this talk. So this work was actually very much inspired by the work on approximate group by Udi and also Green and Bullock and Tao. It is a collaboration with Chin Pong An, Yifan Jing, and Hrushovski Chang. So these are probably not very familiar names because they are not people in our area. So Chin Pong is a lead group theorist at Peking University. Yifan is a combinatorialist at Oxford, and Hrushovski is a harmonic analyst at Berkeley. So we are looking at expansion in a group. So throughout, we would let G be a group, and for X and Y subset of G, we would let X, Y be the product set. And when G is an additive abelian group, we will write X plus Y instead of X times Y. Let us start with a really simple example. So let's say that we are looking at the real number together with the Lebesgue measure mu. And if you have A and B in R with A smaller than B, then if you look at the sum set of these two, that could be just the interval 2A and 2B, right? And in other words, you would see in this special case that the measure of this sum set of the interval AB with itself is 2 times its own measure. And so if you the same AB mu as above, and if you choose a compact subset of the interval AB, and let's say that this compacted subset, it has measure greater than 99% the measure of the interval, then if you're looking at the sum set of X with itself, the measure of the sum set is at most the measure of the interval 2A, 2B, and therefore smaller than 2.1 times the measure of X. So that allows us to ask some really natural question. So first of all, is there a compact subset of X such that the measure of X, the sum set of X with itself is strictly smaller than 2 times the measure of X? And other than the compact interval, is there another example that you have the expansion exactly to? And number 3 is that some essentially different example from the one above that the measure of the sum set is smaller than 2.1 times the measure of X. And if you think for a little bit, probably you would convince yourself that the answer to the first and the second question would be no, right? Because if you are taking an interval and you sum it with itself, you will see the most overlapping and as a consequence, the least amount of expansion, right? So the answer of 1 and 2 should be no, right? And perhaps that would, from that you can believe that answer in 3 would be also no, right? But perhaps it is a little bit less clear. And in the, that's the case. So the first 2 no answer are essentially the so-called one-dimensional case of the Minkowski inequality, which precisely saying that in general, you have the measure of X plus Y need to be greater than the sum of their measure. And the equality can only happen if these are interval, right? So in the case that X is equal to Y, that is precisely the case that we considered earlier. And so the last no is a little bit more involved. It is a folkloric consequence of the so-called 3K minus 4 theorem by Feynman in additive combinatorics. And this was pointed out in the paper by Mike Chris. So I probably won't go too much into this. So with that, I can introduce the Kemperman theorem. So Kemperman theorem essentially saying that the expansion 2 is minimal in every single word that we are considering. So a natural place to look at that is locally compact group. So if you want to keep some of them in mind, you can think of the real number, the torus, or SL2R, or any Lie group, right, or SL3R. And an example of locally compact group is not a Lie group, is say the additive group of the p-adic integer, and so on and so forth. And such locally compact group, it can be equipped with a left half measure. Well, the most important property is that so the measure, the set X is always equal to the measure of the left translation of X, right? So for instance, if you're looking at T squared, this the left half measure, you can choose T squared is R squared quotient by G squared, right? So you can choose the left half measure to be a multiple of the quotient half measure, for instance. So one issue with the left half measure is that sometimes it might not be right invariant, right? So translation of a set to the right, it might change the measure. But in a lot of cases it is. So for example, when the group G is compact or a nilpotent Lie group or semi-simple Lie group, the left half measure is also the right half measure. And in such case, we call such group G unimodular. And for convenience, we would assume that the group G in this talk is unimodular. So the theorem by Kemperman says that if you are taking a connected unimodular locally compact group with half measure mu, and if you choose two non-empty and compact set, then the measure, the product set, is greater than the minimum of the measure of the sum and the measure of G, right? So if you are thinking about it, in the case of the real number, this recover the first one-dimensional case of the Minkowski inequality, right? Because in that case, the measure of the whole group will be infinite, right? Which is automatically greater than this sum of these two measures. But in general, we need to include the minimum of this and the measure of G because there's no set such that the measure of that set can be greater than the measure of G, right? So we need to include this. So in particular, the measure of X squared needs to be greater than or equal to measure of X and the measure of G. So perhaps I should pause here and ask if there's any question from the audience, and feel free to stop me to ask anytime if there's a question. All right. So if no, then let me move on. So the Kemperman inverse problem, in some way, it asks for the pretty obvious question, right? So it say that, okay, what can be said if you know that the equality of this happens, right? And that was asked by Kemperman in '64. More recently, Prisma and Tao asked sort of like the question with error. So what can be said if equality nearly happened, right? And in other words, there would be a certain small delta such that the measure of product Z is smaller than measure of X plus measure of Y plus an error term. The error term is delta multiplied by mean of measure of X and measure of Y. And we want to say that it's strictly smaller than the measure of G. Okay, so in some way, this question by Prisma and Tao is a natural progression of the question of Kemperman. So maybe it's fair to say that this is called the inverse Kemperman problem. And we also have the symmetric version, right? What can be said if the measure of X squared is just 2 times the measure of X? And what can be said if the measure of X squared is smaller than 2 times the measure of X plus a little error term? So if you think about it, okay, so maybe let me pause again and ask any question from the audience. All right. So if one thing about it, so if the measure of X and the measure of Y are both larger than half the measure of the full group G, right? Then according to the Kemperman, this Kemperman inequality, right, you would see that the measure of X, Y must be exactly the measure of G, right? Because mu X plus mu Y is bigger than mu G, right? So in such case, you really cannot say something too interesting about the structure of the set X and Y, right? Because in anything, the equality would satisfy trivially. So to avoid such situations, so we need to stay from the measure of G over 2, right? So let's stay really far away from that. Assume that the measure of X and measure of Y is strictly smaller than measure of G over 3. So in this case, you are just having the nice part, the measure of X, Y greater than the sum of that measure. And okay, so let us make certain guess of what should the answer be, right? So the most optimistic guess that you can think of is that the group G must be the real number and XY must be more or less the interval, right? But you can see that immediately that this is not quite true, right? So for instance, you can take G to be equal to the torus, and you can choose X and Y to be small interval, right? So in some way then you can perhaps convince yourself that the measure of X times Y in that case is just a sum of two intervals, and that is equal to the sum of the measure of X plus the measure of Y. Yeah. Okay, so maybe just the real number and the torus together with interval. Okay, but again, once again, this is not correct. So there are other situations when equality happen. So namely, for example, if you can take G to be, you can extend the torus with compact group, right? Say SO3T, right? And then you can choose X to be SO3T times an interval and Y to be SO3T times another interval, right? Then one can also check that the equality happens in this case, right, by using Fubini theorem. So essentially, the situation is a trivial extension of the earlier situation. So more generally, you can the equality can happen if somehow you have a continuous surjective group morphism from the group down to the torus with a compact kernel, and you choose X and Y to be pulling back the inverse image of two interval, right? So perhaps to have you see this picture in a more clearer way, let's draw a picture. So you can think of the group G at this rectangle over here, and you have a projection now to the torus, which I can think of it as this line over here. And I choose two interval I and J, and I look at the inverse image of I and J, right? So in this case, probably you can convince yourself that if you are taking the product of X and Y, you will get the inverse image of I plus J, right? And therefore, in this situation, you will see that the equality indeed happened. So this could be an optimistic guess, but more reasonable. So this is still say that essentially the interval, the torus and the real number together with intervals are the only example, right? But we need to do the obvious trivial modification to the statement to avoid the obvious pitfall. And for equality nearly happen, maybe you can have the same. So the natural guess is that you will have the same picture with some perturbation. Yeah. Okay, so once again, I would pause a little bit to ask if there's any question. Okay, so this turned out to be not such a terrible optimistic guess. So it was proven correct in a lot of situations before our work, right? So for equality problem for abelian group, which was proven by Knieser in 1954, right? And if you think about it, this is even earlier than Kemperman paper, because Knieser also proved abelian version of Kemperman result. The near equality problem is much harder and only been considered recently. So for T to the D, this was solved by Bilu in 1998 with sub-exponent bound. And okay, there's some improvement for the case of one torus by Candela and Roton. A near equality problem for compact abelian group. This was only done by Tao in the 18 and using non-standard analysis. But okay, to be fair, this can be really standardizable and it's give a quick bound. And Chris and Iliopoulou gave a sharp and effective bound for this in 19. And for non-compact group, this was solved by Christmer in 19, also using non-standard analysis, but in a more serious way and cannot be made ineffective. All right, so without further ado, let me state the Augment theorem. So the earlier reasonably optimistic guess that we gave just now are correct. And this was proven in 3 papers. So we just finished this project recently, and it took us more than 150 pages. The first paper in 2020 handle the equality and near equality case for a compact group G. After that, we have an intermediate paper where we develop some tools, and that is a paper on non-trivial Minkowski inequality. And finally, we with that recently, we are using that tool, we handle the last case inequality problem for non-compact G. Okay, so since this is pretty long, so there's no way that I can explain everything. So the goal for the rest of the talk will be, I just want to explain informally the strategy for the first paper, maybe with some focus on from the idea from logic. If time permit, I would say a little bit about the other two papers. Okay, I won't say anything about ongoing work. Right? But once again, if there's any question, feel free to stop me. Okay, so because the non-compact case is better handled by the second and third paper. So for the next part, we will just focus on the case where the group is compact, and in particular, it's automatically unimodular. And recall that we already assumed earlier that G is connected, right? Maybe I didn't explain the connected assumption for earlier on, but if you have the group that is non-connected, you can just choose the connected component, and the Kemperman inequality will not be valid, right? So you need a connected assumption. And we will also restrict to the symmetric case where x equal to y, and we again we assume the measure of x is smaller than the measure of g over 3. And from the data that the measure of x squared, so we know that the measure of x squared is nearly 2 times the measure of x, right? And we need to do two things. We need to construct a group morphism from the group G into the torus, and together with a compact interval subset of G such that X is inverse image of that interval, right? So in other words, we want approximately to have approximately this picture. Yeah. So the proof, the structure of the proof, this has 3 main steps. So the first step is we want to reduce the problem to a Lie group with bounded dimension, right? So in other words, we want to obtain a Lie group L with dimension smaller than Lie. This is independent of the group G and the set X, right? Together with certain Haar measure. Okay, the Haar measure on L has Haar measure mu tilde, and we want to construct the group G into L together with compact A in L such that X is close to pi inverse A, and the measure of A squared is nearly equal to 2 times the measure of A. So in other words, we really want this picture, right? But we do not have, we not go all the way down to the torus. We only going down to a Lie group with bounded dimension, right? But we want this picture, so it is like an intermediate step where you are starting from locally compact group, you're going down to a Lie group with bounded dimension. And this step used model theory, or more precisely the theory of approximate group together with one new geometric idea. All right, but after that, you need to go from the Lie group down to the torus, right? And for that, the key idea is the machinery is somehow you want to construct a pseudometric. So a pseudometric with a some gap suitable property, and a pseudometric, you can think, okay, a pseudometric is, it has the same axioms as a metric, except that we are relaxing the condition that if 2 points have distance 0, they must be equal, right? Right, so maybe I would go back and explain a little bit further later on why we want a pseudometric. And in step 3, so you want to reduce the problem to constructing a pseudometric with a certain suitable property. And then in step 3, you leverage on the structure, the fact that we are handling Lie group, we leverage a little bit on the structure of the Lie group to showing that if you are looking at this this symmetric difference between the translation of the set A, this could be of pseudometric that satisfy the behavior that we want. Yep. Okay, so once again, I would pause over here to ask if any question about this step. Okay, so and this use okay, so maybe before we go ahead, let me mention one of the fundamental difficulty between a non-abelian problem and the abelian problem is that so actually these situations are quite different from one another. So the optimistic guess in the non-abelian case, it imposes a heavy constraint on both the group and the set. So for instance, so according to our theorem, right, you would never be able to find a set with expansion 2 in SO3R, right? Because simply because there's no continuous surjective group morphism from SO3R to T, right? And our theorem saying that if the measure that's expansion 2, then you need to have a map to T. And but in the abelian situation, it's quite different, right? Because for any compact abelian group, you can always find a group morphism into the torus, and using that you can construct the inverse image to obtain a set with measure expansion 2. And and this has a consequence for our difficulty. So in the abelian case, the central tools is Fourier analysis, and this completely breaks down in the non-abelian case. And we need to use new tool, right? So heuristically, somehow we need to replace approximate Fourier analysis with some kind of approximate representation theory to be able to handle this kind of situation. But it's not all bad because there are some application of the fact that the non-abelian case is different from the abelian case. So from our result, we can deduce that in non-abelian, in SO3, for instance, you see that you have a measure expansion gap. So you have the least measure expansion need to be something like 2.10 to the power 17, right? Which is quite different from the case in R. And we also have similar expansion gap for other semi-simple Lie group as well. And this is one of the results to work a conjecture by Brulak and Green with conjecture that in SO3R, you have the measure expansion gap of near the measure expansion need to be at least close to 4, right? So so the trivial bound is 2, right, by Kemperman. But here we can improve a little bit, okay, even though that is still pretty far away from what we would like to have. Okay, so back to step 1. So recall that we want to construct a suitable Lie group L and a group morphism from G into L. And the idea is to connect our problem to the works of Hrushovski and Brulak, Green, and Tao on approximate group. And this is another place where Fourier analysis fails and model theory somehow come to help. And in fact, if we think about it, the two problems are quite closely related. There is so if we are relaxing the condition, okay. So over here, with one, the measure of x squared smaller than 2.1, the measure of x, right? But if we are relaxing the condition to saying that the measure of x squared smaller than k times the measure of x, what you get is the Feynman inverse problem for the group G, right? Which asks for the structure of such a set X. For our purpose, we will call such a set X a K small measure expansion set. And there is a closely related notion of a K approximate group, which imposes that the identity needs to be in X, X needs to be symmetric, X inverse equal to X, and X squared can be covered by K many left translate of X. And it is clear, you can see clearly that a K approximate group must be a K small measure expansion set. But there was a theorem of Tao which saying that these two notions are really close. So if you have a small measure expansion set, you can produce a closely related K approximate group. So because of that, in some way, we can think of the Kemperman problem as the extremal version of the Feynman inverse problem, right? Which is more or less the same as the problem of classifying K approximate groups, right? So notice that in this case, we have a stronger assumption, right? Namely, K here is almost 2, right? But we also want a much stronger conclusion, right? To appreciate the relationship between many of these problems, so perhaps let's look into a situation of like the group of P element. So the group of P element is not quite, it's not connected, right? So it's Kemperman inequality does not quite apply to it. But notice that on the other notion of like approximate group or the notion of small extension set, you can still define for this situation. In this case, the analog of the Kemperman inequality is a theorem by Cauchy and Davenport, which saying that if you look at two non-empty finite subset of this, then the size of the sum need to be at least the sum of the size minus 1 and b, right? So the minus 1 over here is coming from the disconnectedness in some way. And in particular, the x plus x is greater than minimum of 2 times x minus 1 and b. And the analog of our result in this case is a theorem by Vosberg, which is saying that if let's say that if you have x plus x is equal to 2 times x minus 1, then x must be an arithmetic progression, right? So arithmetic progression is the analog of an interval in this situation, right? If you are relaxing the condition, instead of 2, you are changing it to k, then a theorem that along this direction that we want is a Feynman theorem, right? Which saying that if x plus x smaller than k times of x, then x must be arithmetic progression-like, right? And arithmetic progression-like means it needs to be contained in a generalized arithmetic progression with a bounded dimension and the size at most bounded constant multiplied by the size of x. So the modern proof of the Kemperman of Feynman type theorem, just like the solution of the Kemperman inverse problem for a Minian group, this use tools from Fourier analysis. So let me tell you how it is used and perhaps maybe why we need to replace it. So Fourier analysis, the role of Fourier analysis is that it somehow allows us to approximately construct the so-called Lie model. Okay, so a warning over here is that this is not model in the sense of model theory. So what does it say? So first of all, starting out from a group G with a set X, and let's assuming that the measure of X squared is smaller than K times the measure of X. So first of all, there is this argument called the good model argument, which allows us to approximate it with a pair closely related G prime, X prime. That also satisfy a related condition, right? And the point is that once you do this approximation, you can now use Fourier analysis to construct a group homomorphism into a d-dimensional torus, right? Where the dimension d is being bounded by the constant that is independent of G and X, right? Together with a convex set A such that X is closely related to X, to the inverse image of A. And then after that, we extract out a generalized arithmetic progression of a certain dimension just from this convex set, the inverse image of the convex set. So let me show you a picture, so to perhaps make it clearer. So for the group G over here, you somehow try and, okay, so after trivial modification to make it good, you would be able to construct a map down into T to the D together with a convex set A, right? Such that X is not the full inverse image, but maybe 20%, right, or 10%, right? But this picture is quite similar to the picture that we want, right, in our theorem, right, but weaker in several aspects. So instead of instead of the torus as the image, we only have a bounded dimension torus, right? And instead of the set A that we want to be an interval, we only have a convex set, right? But you can think of a convex set as somewhat higher dimension interval, right? And instead of having X to be the inverse image, almost only the inverse image of A, we only have X contain a positive proportion of the inverse image of A. So we want the non-abelian. So in order to get the result to answer the Feynman theorem for non-abelian group, we need to have, we want the same kind of picture. We want a similar kind of Lie model theorem. But the problem is that Fourier analysis no longer work, right? Because Fourier analysis just tell you just discussing group morphism into torus, right? And if the group that we are starting with is SO3R, right? You have no such group morphism. So this breakdown. So the idea is that somehow we need to replace this approximate Fourier analysis with some kind of approximate representation theory, whatever that is. So actually no such theory called approximate representation theory has been entirely developed yet. And the reason that this is, I call it approximate Fourier analysis instead of Fourier analysis is because in the first step over here, you are approximated. So you cannot use Fourier analysis directly, but you need to approximate it to get some kind of good model. Okay, and this is where somehow model theory come into the picture. And the heuristic over here is that under certain kind of structure assumption, okay, maybe before that, what we really want to do is we want to construct something to a group, Lie group with bounded dimension, right? So that means that we want to construct a representation with small dimension, right? And the heuristic is done under structure assumption. So for example, stable and NFP and so on and so forth, there could be suitable low dimension representation. And the stereotypical theorem of this type is the solution of Pillay conjecture by Hrushovski, Petersill, and Pillay. And also the later compact domination theorem by Hrushovski and Pillay. So this saying, so informally, it is saying that if you are looking at a definably connected, so you can just think definably connected, you can just think of it as connected, right? And definably compact, you can just think of it as compact. In a sufficiently saturated or minimal expansion of a field, and then if you are take a set X which is definable, and let's say it has full dimension, so same dimension as the dimension of X with respect to the minimal dimension. So you have the pair of GX. It would look like a Lie group together with a closed set in certain way. And more precisely, we need to take this set G00, which is the element of on the infinite estimable element. Okay. So the precise definition is that this is the smallest type definable subgroup with bounded index, right? Then G over G00, this is a Lie group with dimension or minimal dimension of G, right? So moreover, so with this map, the quotient map, you know that X is closely related to pi inverse of A. So somehow, so this theorem is, okay, from this point of view, what we are doing is starting from a very huge object, right? This group G together with X, a huge object in a very transcendental world. Somehow we are obtaining a representation in a group such that the dimension of this group is bounded, right? Namely related to the minimal dimension of the original group. So let me also show you the picture. So picture over here is that if you have a group G over here, and you are, so this is telling you that your set X after G quotient G00, it looks like this, right? So it's not perfectly an inverse image, right? There could be error of smaller dimension set, right? But Well, and then you can think of this in this combinatoric lingo as saying that the set Gx over here, it has this Lie model G tilde and I. And just judging from the picture, this is very similar to the statement we want to prove, right? And that there are many other statements of the same flavor in model theory. And one of them is the result by Hrushovski Lie model theorem, also known as stabilizer theorem. If you take you view it from model theoretic point of view. So this saying that if you are taking a family of approximate group with increasing size, and you are taking the ultra product of this, then okay, up to some caveat, this G(x) has a Lie model with bounded dimension, right? So in some way, we are having a picture that are really similar to the earlier picture, right? Except that instead of T to the D, we are having a Lie group L with bounded dimension, right? Which essentially coming from the non-abelianness, right? But other than that, the picture looks pretty similar, right? And if one thing about it, why do we need to take ultra product? So this theorem can be read as saying that if you have a sufficiently large finite approximate group, you will be able to construct certain kind of like approximate or quasi group homomorphism into a Lie group, right? But if you are taking ultra product, right, all this error disappear and this become an honest group homomorphism. So essentially, the key insight over here is that in some way you can view this K approximate group as assumption as a structure assumption in the sense of model theory, and because of that, many of the machinery of model theory can be similarly developed. And okay, so Hrushovski Lie model was then used by Brulak, Green, and Tao to show that K approximate group are closely related to the so-called coset mu progression, which is strictly generalizing arithmetic progression. And in some way, the argument proceeds in a parallel direction with the abelian argument, except that there is no good notion of convex set over there. So the new idea over there is somehow you need to replace it with the appropriate analog of convexity, and in this case, it's the notion of this strong approximate group. All right, so let's get back to our problem, right? So in our problem, what we need to do is we need to obtain a Lie group L, right, with the dimension L smaller than D, right, together with a set A such that X is almost the inverse image of A. And so this would require making link to the theorem approximate group plus one new geometric idea. So to make link to the theorem approximate group, just now, so there is this standard yoga by Tao, which so over here we just have small expansion set, right? Smaller than 2.1, the measure of x squared is smaller than 2.1, the measure of x. So by a standard set, we can produce from it an approximate group that has size comparable, right? So we are not really in the context of a finite group. So we need to use generalization of Hrushovski result for locally compact group, but that was already obtained by Carolino. And using that result, which is so the generalization of the result to locally compact group, we get the group L and pi. So maybe let's summary in the summary of the picture, what we get is that we managed to get from our original group G into a Lie group L with bounded dimension, such that X is the inverse image of, let's say 10% of the inverse image of the set I, right? But that is not good enough, right? So really we want to say that the measure, so X is almost everything, right? So you want to say that on the white space over here, essentially there's no white space. And the new geometric idea over there is that Hrushovski theorem, essentially. So by Kemperman theorem, if you are looking at the set I, you already see that the expansion is 2, right, by Kemperman theorem. And you can see that if the inverse image is not almost everything, there will be expansion vertically and that's expansion horizontally, and that would make the measure expansion much larger than 2 times the measure x. And that could be a contradiction, right? So actually the idea is really simple. So the geometric argument. So with that, in some way, we have proven a cross result along the line of the theorem that we want, right? But now we need to go down into the torus. So for that, so in the step 2, we need to, okay, so conceptually, what we really need to do is, okay, so now we no longer can take ultra product, right? Because we want a very effective result, right? We don't want to just take ultra product. And the idea is that somehow we are developing a small piece of approximate representation theory directly. So we would do a little bit of approximate representation theory directly. So, so in the step 2, we need to construct, we reduce the construction of the group homomorphism that we want and the interval to obtaining a pseudometric on the group G, which is almost linear. So almost linear here means the distance between 2 elements G1 and G2. So if you have 3 elements, the distance between G1 and G3 is either the sum or the difference between the distance of the G1, G2 and the distance between G2 and G3, right? That is to say that every 3 points need to almost live on the straight line, right, according to this distance, right? So if G2 is in between G1 and G3, you will see that it is a sum, and if not, you will see that it's the difference. And conceptually, so let's think about it. So essentially, we want to construct a group morphism from the group G into the torus, right? So somehow we want to construct a representation, right? So of group, right? So the idea is conceptually we want to first construct the group morphism from the Lie algebra, right? Approximate Lie algebra group homomorphism into from the original group to R, right? Which is the Lie algebra T. And this pseudometric, one can think of it as conceptually as such a Lie algebra group morphism. And this almost linear pseudometric, in some way, it would remember the correct group morphism locally with some error, right? So to get back the full group morphism, one needs to do certain kind of summation or integration altogether. And except that after one do that, one end up with an analytic multi-value almost group morphism. And we need to somehow extract from this a continuous single value group morphism. And that is done with a little bit of help of descriptive set theory. So from multi-value, you can get a single value using measurable selection theorem. And you are getting a group morphism which is universally measurable, which is not quite continuous, but pretty close. And then after that, you use a theorem by Grove, Ketcher, Root, and Gaston to approximate this almost group morphism with a universally measured group morphism. So you get from an group morphism with some error into a group morphism, right? And I mean, after Udi lecture yesterday, you can think of this step as saying that in this particular situation, on this bounded cohomology just vanished, and then you get an actual group morphism that is very near to the almost group morphism. And then after that, it turned out that the group morphism that we constructed is already automatically continuous by a theorem by Rosendahl and automatic continuity theorem. Okay, so there's a subtle automatic to control the linear correlation, but probably I won't go into that. All right, so finally, we need to start from the group G, and we need to construct the design pseudometric. And in that, we need to look at this pseudometric that is defined by symmetric difference, and we need to show that this is almost linear. So basically, we need to show that this is an approximate Lie algebra homomorphism in some way. And so as an intermediate step, we need to use a probabilistic argument to showing that the set A is not too complex, and it needs to be termed in a geometric way in the sense that it cannot be a so-called Kircheia set. So a Kircheia set is a set that is, it looks geometrically, it's very complicated as it contains a line segment of full length in every direction, even though it has a very small measure, right? And we want to show that this kind of object cannot happen, right? So in other words, you want to be able to find a certain torus sub. Okay, so this notion of Kircheia set needs to be defined carefully, a little bit carefully, and then that is defined in terms of coset of a one-dimensional torus subgroup. So after this, you achieve a one-dimensional torus subgroup such that on the translation of this one-dimensional torus subgroup intersect your set A or X originally in a set of very small measure, right? And then we use a geometric argument in step one. You get more information about the set, the geometrical shape of the set A. We learned that A need to look like just like a strip, and moreover, any translation of A it need to look like a strip. And because of that, to understand the behavior of this, the intersection of measure, you can look at it in the intersection with a generic left translation of your torus subgroup, right? And you are just reducing to essentially two intervals over here, and that allows us to prove that this is almost linear. And that complete the first step of the final step of paper one. So how many more minutes do I have? Can I just talk for another 5 minutes?
Yes, no problem.
Thanks. So let me continue for another 5 minutes. So let me just briefly mention what do we do for the case that is non-compact. And at first we thought that this is much harder, right? Because we thought that, representation theory for non-compact B group is just terrible, right? And another problem we run into is that even if we can construct approximate group morphism into R or whatever, it is known that there might be no nearby group morphism, right? And as a consequence, we need to develop a completely different kind of tools. But the current view is the non-compact problem is less difficult, but it requires different tools. Okay, but that said, so after yesterday's lecture, there might be a chance that one can overcome this difficulty and use the same proof to prove also the non-compact case using this kind of like bounded cohomology. But maybe that currently that is just a hope. But let me tell you how did we trying to prove the non-compact case. So for the non-compact case, so first of all, let's come back to this Minkowski inequality, right? So just now, Minkowski inequality is saying that if you take an interval, the measure of the interval with itself expansion is 2, right? So instead of in R2, you will see that the smallest measure expansion is 4, right? Because there's 2 dimensions, right? Given by a square, right? So if you take a square and you take the product with itself, it will expand by 4 times, right? So in R3, the expansion is 8, and so on and so forth. So in R to the D, the expansion is 2 to the D, the measure, the original set. And if you think about this, is the conclusion over here is stronger than the conclusion of Kemperman inequality when D is greater than 1, right? You can also ask for the inverse, this inverse Minkowski problem, and that was studied by a few people. okay, one can also ask, is there a suitable generalization of this Minkowski for locally compact group? And the naive guess of such a generalization would be that if you are looking at the locally compact group, okay, we need to assume connectedness, right? So connected locally compact group with dimension, okay, you don't even need that. Okay, just locally compact group. Then the measure of the expansion is 2 to the d, right? Where d is the dimension of the locally compact group, right? But that turned out to be too naive. So for example, like if you are taking your group to be SL2R, right? So SL2R is of dimension 3, and you can visualize the region as the interior region of the torus, right? So, and SL2R, it has a compact subgroup that is SO2R, and SO2R, you can think of it as the circle at the center. So if you are choosing X to be a small neighborhood of this circle at the center, you can show that the expansion over there is roughly 4, right? So somehow this compact, you will see that there's an overlapping again when it's compact, and the compact dimension over here doesn't contribute anything to the expansion, right? So over here just 4 instead of A, right? So 4 is 2 squared, and A is 2 cubed, right? It has topological dimension 3, right? So that lead us to define the notion of non-compact dimension to be the dimension of the full group minus the dimension of maximal compact subgroup. And the conjecture, the corrected conjecture would be the measure in such a, okay, so let's say we are having for unimodular case, so the measure of x squared would be greater than or equal to 2 to the n the measure of x, right? So instead of dimension, it's just the non-compact dimension. Well, so we couldn't fully show this conjecture, but we can show that we can reduce it to the case of simply, okay, the first result, we can reduce it to simply connect the symbolic group, right? And the second result is that we can show this conjecture with certain effect. And the effect over here is on this helix dimension, which I'm not getting to it. But in many cases, this defect is equal to 0. So for example, in all the case of matrix group, the defect is 0. And the real thing that happening behind is that if you're looking at the semi-simple part of a matrix group, it has finite center, right? And in the case of finite center, H would be equal to 0. So in the case for matrix group, we obtain the full conjecture. Okay, so in the last paper, so we are studying the structure of locally compact group with this n minus 8 is smaller than is bounded. So we get the following dimension bound. So if you have a set with expansion smaller than k, then there must be a morphism into a Lie group with dimension at most log 2, the integral part of log 2 of k multiplied by the integral part of log k plus 1 over 2, right? So then we can apply to the case that k equal to 2.01, right? And if you look at 2.01 over here, log 2 of k, you get 1, and over here you get 2, right? So 1 multiplied by 2 divided by 2, you get 1, right? And the only group with dimension 1 is R, right? If it's non-compact, right? So if you have a map down, then the group that you get needs to be non-compact because you're assuming that you have a compact kernel. So the only one that has is R, right? So you get a map from G to R, and then you can finish off using the technique from the earlier step 1. Okay, so recently, okay, so maybe 2 comments. So one comment is that if you are agreeing that this assumption is the measure of x squared smaller k measure of x as a kind of like structure assumption or NIP assumption or whatever, then this theorem, it has the kind of similar form as a kind of Pillay conjecture, right? So from a very big group, you have a quotient that is small, right? So you have a small dimension representation. And also this theorem was applied by Van Loo, Udi, and Machado in studying of some variation of approximate group, which very likely you will see tomorrow. All right, so that's all that I have for today. Thanks for listening.
Thanks, Minh. So are there any questions? maybe online.